They're my favorite.
Yay.
All right, so yay, the next part of waves, in fact the last part of waves, is optics. And we're going to be in optics for like 3 weeks. It's really cool. There's some neat stuff in optics. I wish I had more stuff I could play with optics, but I have various things around the room. This hopefully will work since Sean gave me a really cool pencil sharpener. But did we do this earlier this year when we did pressure?
Whoa.
Yeah, this one leaks a little bit. This one doesn't leak, which is pretty cool. This one leaks a little bit. It depends on how sharp the pencil is. But it's kind of neat. You can actually look at it and you can see some serious refraction. So that's one of the things we're studying in optics is refraction. So I'm going to put this one in the sink. I'm going to put this one right back here because this one is still intact. Last year we got like 30 or 40 pencils into one bag. It was awesome. We got like 30 or 40 pencils. Kept putting them in there and putting them in there and putting them in there. If you're curious about why the water doesn't leak out, then that's a discussion for fluids. But if you actually look at the pencil, you get to see some pretty neat stuff. I'll let you pick it up. If you want, you can come pick it up. Just realize that if you spill it on yourself, that's between you and whoever's going to laugh at you on the bus. Okay, so optics is the study of how waves move when they go from one medium to another medium. And so we're going to look at prisms. We're going to look at refraction. This is a very important principle we'll talk about. And if you're wondering why wave energy, transverse wave energy, slows down when it goes into a medium, this is a pretty good model. So when wave energy just travels through a vacuum, it just cruises along at 3 times 10 to the 8th meters per second. Pretty good. However, when it goes into a material, that material has to absorb the wave energy, pass it from atom to atom to atom to atom to run out of atoms, and then spit it out the other end. So it's gulp, and then it goes vibrate, 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 and then spits it out, and then gulp, and vibrate, 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 and spits it out, which takes time. So that slows light down. Light moves slower in a medium, which is why diamonds sparkle. We'll talk about that a little bit later too. Now this is a very important diagram which we're going to revisit quite a bit next time, but I want to talk about this idea first. So fish is in water, cat is in air, because fish don't go in air and cats don't go in water. For this left diagram, is the fish looking at the cat or is the cat looking at the fish? The left diagram. Is the fish looking at the cat or is the cat looking at the fish? Cat's looking at the fish. It's not like in cartoons where there's like looking beams. In cartoons are like, look over there. They show the little looking beams coming out of people's eyes. No. The environment illuminates the fish, and that light that reflects off the fish enters the cat's eye. Do fish emit light? Someone's saying, well, technically, yes. Hopefully you got that question right on the quiz. Fish do emit light. All things that are at our world temperatures emit infrared light. Remember that? You emit infrared light. Remember this? Everything emits infrared light. However, do fish emit visible light? No, they don't. So the environment has to illuminate the fish, and then that light reflects off the fish and enters the cat's eyes. Okay, similarly, in this case, the environment illuminates the cat, and then that light energy reflects off the cat and enters the fish's eyes. And this changing of angle is called refraction. We're going to revisit this for quite a bit of time in a little bit. Okay, any questions before we move on? I have one. Where's my clicker? Okay, moving on. Wave reflections in 2 dimensions. So what do waves do in 2 dimensions? Well, I got a laser pointer here. Boop, 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 boop. I got a tiny laser, a tiny mirror right there. And I'm going to stand over here, right about here, I think is the middle point. And I'm going to shine my laser as steady as I can at that mirror, which hopefully is parallel to the plane of this board. What I'd like you to tell me is, where's the dot end gonna end up? Point to where you think the dot's gonna end up. yeah, most of you realize that if I'm standing in the right place and I hit the mirror, that the dot ends up right over there. Why does it do that? I don't even know. It's geometry. It's a conservation of momentum. It's what happens when energy goes into molecules, energy comes out of molecules. Well, what happens is rays bounce off a plane. So if this is the barrier plane, by the way, in our example, this is the barrier plane, whiteboard, and the mirror right there. We say the incident ray strikes the barrier and is reflected or becomes the reflected ray. So the ray coming in from the laser to the mirror is the incident ray, and the ray going out from the mirror to the wall is the reflected ray. And how that ray reflects is based upon something called the law of reflection. So the ray coming in, the laser beam coming in, striking the mirror is called the incident ray. That's the incident ray. And the ray leaving the mirror, striking the wall, is the reflected ray. Now here's the crazy thing about measuring these angles. They are all measured to a normal. We talked about what a normal was when we were talking about forces. You have a button force down and a normal force up. What does normal kind of mean in physics terms? Opposite and equal? Okay, that makes sense. What else?
Force that resists something.
Force that resists something? Okay, what else? Let's develop that. So normal means opposite and equal, like Newton's third law. Excellent. Force that resists something, like a normal force. Excellent. Okay, a standard. Good. So something that equals out net forces. If you were to represent your chair with a horizontal plane, what direction is your weight? Down. Down. And what direction is your normal force? Up. It turns out normals are always perpendicular to a plane. And it's in the case, in this case as well, the normal is perpendicular to our boundary plane. So if our boundary plane is this plane right here, the whiteboard, where's the normal plane? Yep, running right down the middle of the room. Right down between Samu and Sean. Right between Jerry and Christina. Right between Braden and Leaf. It's the plane running right down the middle of the room. Okay, that's the normal plane. So if our boundary plane is this, the normal plane is this. Angles of incidence and angles of reflection are always measured to the normal. The angle of incidence is measured from the incident ray to the normal, and the reflected ray is measured from the normal to the reflected ray. Okay. They're always measured to the normal. Why, do you suppose? It's a very important reason, and making the math easier is one of them. There's actually even more important reason is why we would always want to measure from the normal to the incident ray and from the normal to the reflected ray instead of from the incident ray to the barrier plane and from the reflected ray to the barrier plane. We always want to measure to the normal. Why? Why do we care about that? Does this surface reflect? James, do you want to answer it?
I was going to say not all barriers are straight.
Exactly, yeah. Not all barriers are perfect two-dimensional planes that are straight. They're not flat. So this object reflects. Not very well, but it reflects. And it's not flat. But the crazy thing is its normal will always be tangent to its surface. So this has a normal. When light strikes it, it still bounces out of normal because you can always find a tangent to a curved surface. See? Can you imagine another? Here, let's make the normal here. Make a T. There we go. Okay. So the pink one is the normal, and the black one's the barrier plane. So even on a curved surface, there's still a normal. It's just perpendicular to the tangent. Does that make sense? When I say words like perpendicular and tangent, does that make sense? Okay, cool. So we always measure to the normal because our surface might not be flat. We might not be able to measure this angle. We might have to always measure this angle, the perpendicular angle to the normal, or to the tangent. Okay. Does that idea make sense? Okay. Law of reflection states that ray coming in, ray going out, they're the same. As long as we have the same medium. Now, if somehow I was able to fill this side of the room with air and this side of the room with water, would you expect the angles to be the same? No, exactly, because I just said the medium is the same. If the medium on this side of the normal is different than the medium on this side of the normal, then we have to use a little bit of mathematics that we'll learn next time. But as long as the mediums are the same, air, air, water, water, jello, jello, then angle of incidence is equal to the angle of reflection. Mirrors. 3 types of mirrors. What do mirrors do?
Reflect.
They reflect. Okay, mirrors reflect. We've encountered mirrors. My 1-year-old knows how mirrors work. He's like, hey, that's not me in there. It's cute, but it's not me.
Sometimes I wonder if I'm the image reflected.
Yeah, that's deep, man. What if the other side of the mirror is the real world? Anyway, moving on. 3 types of mirrors. The simplest mirror is the flat mirror. Okay. Simplest types of mirror is the flat mirror. Flat mirrors are nice because they have zero, the angles are simple. If we take 3 rays, and in this presentation, incident rays are going to be yellow, reflected and refracted rays are going to be red. So if we take 3 rays and we strike a flat mirror, where do those rays go? Yeah, they come right back. They get reflected. So the incident rays strike a mirror. The mirror then refracts or reflects those 3 rays back. Couldn't be simpler. Next type of mirror is a curved mirror. Funhouse mirror. Concave. When something is caving in on you, it's concave. Like a cave. A cave has an opening or a cavity. If there's like a hole of something, use like there's a cavity. It's concave. That beaker has a cavity. It's got an opening. It's curving in on the opening. So concave mirrors curve towards you. Interesting things, concave mirrors. If you take 3 parallel rays and you strike a concave mirror, what do they do? Exactly. Does the law of reflection still apply? Oh yeah, definitely does. It's just the barrier is now like that. There's the barrier there, there's the barrier there. And the barrier plane just, it changes with where you are on the mirror. You need another here. Pencils. Okay. So the barrier plane changes with where you are on a concave plane. So the rays, they do something kind of cool, Gesundheit. They converge. The rays converge to a point. It's a concave. What's the other kind of mirror called? Convex. Convex. Yeah, convex. You're like, you vex me, go away. That's how I remember it anyway. Convexes are surfaces that curve away from you. A bowling ball is a convex surface. So a convex mirror is one that curves away from you. So when those same 3 rays strike a convex mirror, what do they do? Yeah, they go out. Okay. The barrier plane is still there. It's just the barrier plane is now, once again, follows the curvature. Yeah, they go out. They do something called diverge. The rays diverge. Two roads diverged on a whiteboard, and I chose the one that was less traveled. They diverge. Why are you breaking up with your boyfriend? Well, our ideas kind of diverged. Our lives were going in different paths. I wanted them to converge, but they diverged. All right, moving on. This thing in the middle of the mirror is called the principal axis. And this is where we're going to anchor our diagrams when we're doing ray diagramming. We're going to do a lot of ray diagramming this week. It's pretty fun. Sharpen those colored pencils. We're going to have a lot of diagrams. I really like doing ray diagramming. Some people think it's a lot of fun because it's kind of like drawing. But other people are like, this is more like math than drawing. That's called the principal axis. The point where the rays converge is called the focal point. Like the focus point, the focal point. So there's the focal point for a concave mirror. Should be pretty obvious. They come together and they converge at the focal point. But where's the focal point of a convex mirror? Exactly. It's over here. If you can imagine the rays kind of coming back. Because if they didn't converge somewhere, there would be no image. But you've seen these kind of mirrors, right? Where do you see a mirror like this, a convex mirror? Funhouse? There's one like 200 feet away. James?
Oh, in the library.
In the library. Okay, question?
Where's the focal point on the left?
It's actually on the mirror itself. Some physicists will say there isn't one, but we usually say it has a focal distance of 0, meaning it's on the mirror. But yeah, library. So you find a principal axis, or you find a convex mirror in a library, also in 7-Eleven and in Walmart. Yeah. So that curvy surface where you can see around the corners in Walmart, or they can see the shoplifters in 7-Eleven. Yeah, they used to have them in the mirror in the library so they could see the kids making out in the library. Yep. Right over there. But now the big shelves are gone. But yeah, that's where you see. Now, have you ever looked at one of these? Do you not see an image? You do see an image, but it is what? It's tiny. It's tiny. It's like behind the mirror. So yeah, the focal distance of a convex mirror is back here. And we're going to learn the idea about virtual and real right now. Okay, so here's our flat mirror. And then what in Dalmatian is our object. There's our Dalmatian. And what in illumination? And then what in reflection? Where's the light going to reflect? Back. So you're the Dalmatian, and you see the light bounce off a mirror. But you all know, because we've all grown up with mirrors, that where does the image appear? On the mirror?
So it looks like.
In your eyes.
Okay. Mirror. Sorry, it's so dirty. Doesn't it look like there's another classroom back there? Yeah, so it looks like, okay, if I'm 2 feet away from the mirror, that handsome devil's 2 feet beyond the mirror. Inside the mirror? Ooh, it's like the phantom zone coming at you. So yeah, the image is behind the mirror. Now, since the image is formed behind the mirror, we call it a virtual image. This is the single most complicated thing in optics. What things are real and what things are virtual. Now, if you do internet tutorials, you talk to people, they will all tell you crazy things. They'll want you to memorize stuff. Like, well, it's a virtual image if it's behind this type of mirror, in front of this type of mirror. It's a virtual image if it's behind this type of lens, in front of this type of lens. Here's the trick to whether or not something is virtual or real. If the image forms where light is, it's real. If the image forms where light is not, it's virtual. light do to a mirror? It reflects. So the light's over here, but your brain puts an image over here. Therefore, it's a virtual image. If an image forms because your brain is trying to make sense of information, it's a virtual image. If an image forms because your brain sees light where it's supposed to be, it's a real image. Okay? Again, I don't want to make this thing more complicated than it is now. We're going to move on and discuss it. But in general, the rule is if an image forms where the light is, it's real. If an image forms where the light is not, it's virtual. Concave mirror. There's a concave mirror. There's our Dalmatian. The environment illuminates the Dalmatian. Light reflects off the Dalmatian, strikes the concave mirror. Where does the light go? Back together, and it converges. Since the image is formed where the light is, it is a real image. That's a real image. And there's other words we're going to use to discuss it. We'll get to that later. Yeah.
So then convex would be virtual.
DJ said, so convex is virtual because it's behind it, and that's exactly the case. If you have a convex mirror, light strikes a convex mirror, the light diverges. But we all know an image does form. We take the information that strikes our eyes, we do the trigonometry we learned when we were 2 years old, and we say, oh, there's got to be an image back here. And since the image is back where the light is not, it is a virtual image. I'm going to give you some more words, too. And this is where we're going to end. We have like 3 minutes. We're going to end right here. But I want to give you some more words, so don't pack up just yet. So firstly, if an object creates an image and the image is where the light is, it's a real image. If the image is not where the light is, it's a virtual image. When we describe images we make, when we're diagramming or doing math, we always use 3 words, 3 of 6. An image is either real or virtual. It is either reduced or magnified, sometimes reduced or enlarged. I leave it up to you. I usually just use magnified because it's better. It's either reduced or magnified. In this case, these are both reduced. And then it's either upright or inverted. This is upright, this is inverted. If your reflected rays cross each other, you're going to get an inverted image. If the top ray becomes the bottom ray, you're going to get an inverted image. If they don't cross each other, you're going to get an upright image. In other words, this top ray stayed the top ray, this bottom ray stayed the bottom ray, this is an upright image, this is an inverted image. Okay. Let me cue forward and yep, okay. Yeah. So we'll do the math next time. Are there any questions?